All right, so we are starting a new unit, Unit 5. You all have your books. Looks great. Page 121. So those worksheets just put underneath your book. You're not going to need them until the very, very end. All of our notes today are in the book. We're going to start with quadratics today. So we're thinking, how are quadratic functions different than linear functions? Okay. We're going to do a little warm-up. This is just up here. We're going to talk about it. Okay. It's not in your books. It's up here. Look, observe, talk. This is an example of a quadratic. What looks different about this graph than what we've been doing?
It's going down.
It kind of turns.
It's not a parabola.
It is a parabola. Yeah, that is a parabola. Good. There's a curve going on to it. Okay. This quadratic is showing us height and time for something.
Wait, is that what was the answer?
What?
Never mind.
Okay. So the first question here is how long, let's just say this is a ball. How long is this ball in the air for? Looking at this, can you read the graph? How long is the ball in the air? 4 point. Yes, around there somewhere. Yes. About 4.2, 4.3-ish seconds. Okay, where did you look to figure that out? The X and on the end, where it ended up. Good. Looking at this, can you tell me what the maximum height of the ball was?
77.
About 77, 75. And what did you say at the end? Feet, yes. Don't leave numbers naked. Okay, make sure you tell me seconds or feet or meters or miles, whatever we're talking about, those matter. Good. How did you find that? Where did you look? Good. The top of the parabola, the Y, the highest it went. Good. Last question. From what height did the ball start at? 10, 5, I would say 5. About 5 feet. So we can maybe picture someone that's about 5 foot tall with holding the ball and threw it. That could represent that action happening. Okay. So what we're doing today is we're just going to explore more real world situations. So quadratics IRL is what's happening today. Because I want you to understand what they are before I start making you graph them and solve equations and stuff. So you understand what you're doing. So, starting in our book, we're going to review linears real quick. So nothing to write yet. This is all in your book. It's already graphed for you and everything. This is showing a line. Okay? If we're driving 40 miles an hour, it's a constant speed. It's a linear function. This is what we're used to. We can represent it in a table. We can show it off in a graph. Okay. Looking at that table, how is my distance changing each mile? By 40. That's what makes it the constant, right? Because it's constantly changing by 40 every single time. Okay. So we could even make the equation for it by saying it's 40t, so 40 miles each hour we go by. Okay. Linear functions like this, they always have a constant rate of change. Okay. But what we're going to discover is what happens with nonlinear types. So if linear types have a constant rate of change, which is a fancy word for what? Rate of change. You could do rate of change in just one word. Slope. Good. Yes. Good. Lines have slopes, right? So if they have a constant rate of change, what do you think nonlinears are going to have? Okay, whoever's music is on needs to get turned off and earbuds are out of our ears. So everyone put your hoods down. Put your hoods down. I need to see those ears. Yep. Thank you. So we can probably expect a not constant rate of change. So here we have something different. We have Liam. He is dropping a watermelon from the top of a 30-foot building. Okay? He wanted to know if the watermelon was falling at a constant rate over time. He filmed the watermelon's fall and recorded his observations in the table. So what do you notice about these the rate of the speed of the watermelon? Jenny, what do you see? Height is decreasing. Good. That makes sense, right? Because it's falling. So I hope it's decreasing. What else? How does 300 turn to 283? We went down by what? about 17-ish. We'll round 17, 16-ish. And then how did 283 become 235? Was it 16 again? It was more, right? It's like in the 40s, 50s, 40s. And then it went from 235 to 155. It's even more. The 155 to 42, that's what, over 100? So each time, it's not constant. It actually changes after each second. Okay? So this is the first thing we're writing down. It's on the right side of your paper. So what do we notice? We notice that it's not constant, and it's actually different every single time. Oh, where'd it go? There it is. All right, so you would think dropping a watermelon would be a straight line, but it's not. Why do you think it's not linear? What do you think is making... It's actually getting faster, right, as it's getting closer to the ground? What do you think is making that happen? Gravity. Yes. Science. Gravity makes things move faster as they come down to the ground. And if we threw it up in the air, it would move slower as it went up, right? So because gravity is a thing, it's a real thing, it's going to affect what we're doing. What's up? What? You going to be a student today or just a lump? What you doing? A lump? There's a pencil right there. You see it next to the green marker? Next to the green marker underneath the eraser. You can use that one. Why do you have a little shoe? Oh, it's a key. Is that your little shoe? Okay. So because gravity's a thing, that's what made the watermelon not just drop in a straight line. Fun science fact, you ready? If you dropped a watermelon and a golf ball at the same time from the same height, they're going to hit the ground at the same time. True story. It's true.
But it was an egg.
Doesn't matter. Well, I hope it is. Otherwise, it's a grape. It's not a watermelon anymore. Okay. So, here is Liam's graph when he dropped the watermelon. Okay. What is the independent variable here? Is it the height or is it the time? Those are our two options. Independent. Which one stands by itself? The time. Yes. Our time is independent. That's our x variable. Okay. And dependent. So what depends on the time? The height does. Good. That's a little throwback to last semester. So independent is our time in seconds. Dependent is our height in our feet. All right, he even calculated the equation there for us. I won't make you do that. That's Algebra 2. Algebra 1, we usually give it to you sometimes. Okay, but if you looked at the equation, negative 16t squared plus 300, what do you think that 300, look at the graph, that 300 is representing? The height that it starts, the what part of the graph, Jaguar? The y intercept, yes. So that piece on the end is showing the y-intercept. That'll always be true. The 16, don't worry about it. How about the negative? The negative tells me something. It's going down. Good. So if it was a positive 16, it would be going up. Okay. So those are the key features you only need to worry about right now. Okay. Okay. So this is a nonlinear function. It is called a quadratic function. That's our new unit is quadratics. Okay. A line was mx plus b. A quadratic has a new equation. It is ax squared plus bx plus c, where that a, b, and c, those change numbers. Okay. And we said that that plus c on the end is usually that, well, not usually, it is your y-intercept every time. All right, and I think Melandra knew the name of this graph. What is the graph called? A parabola. Beautiful. Good. Good. Come back to you. Well, it gets confusing because in language arts you learn about parabolas. So it's like it's the exact same word, but it's said differently. So parabola is a language arts term. Parabola is math. I know. It's a teacher's goal just to mess with you. We usually succeed.
Man.
All right. So, y'all okay? Oh. That's social studies. All right. So, Liam's graph. Why did we only look at the first quadrant? So, look up here. So, on that graph on your paper, like if this is a whole quadrant, it only showed us quadrant 1. How come it didn't show any of the other pieces of the graph?
You can't throw a negative.
You can't do negative time.
You cannot do negative time, and you can't do negative, and you can't have negative time. Negative time, negative height, in this problem cannot exist, right? If I went anywhere else besides the first quadrant, I would have negative numbers, and in this situation, we cannot have negative time or height. Okay, good. There are situations where they could go negative. We're going to see those in a second here. Okay.
It's right there.
Okay. So the only reason why, or the reason why it's hidden in only the first quadrant is because we cannot have negative time or negative height in this situation. It's not going to like implode through the ground. And time machine's not there yet. So, can't do it. Me too. I'll go with you. Huh? All right, so in Liam's graph, so I know we've kind of moved on from it, but it's still referring to the graph all the way on the left-hand side on your book right now. In that graph, how long did it take for the watermelon to hit the ground?
Like 4.25 seconds.
4.2, 4.3-ish seconds. Good. Where on the graph did you look for that? Where did we find it? The x-intercept, okay? This x-intercept in a quadratic function, it's called the zero or the solution of that graph, okay? The reason why it's called a zero is because it's when y equals 0, okay? So when your equation equals 0, that's your x-intercept. That's when your y is 0, okay? There is only one 0 in Liam's equation. Where could we possibly have 2? Where could we have a real-world situation where the graph that represents it is crossing my x-axis twice? What do we think? What real-world situation could it look like this?
Somebody make a count.
Someone what?
If they dig something?
If they dig something, okay. What if, so you're talking about like underground?
Digging for dinosaur bones.
Digging for dinosaur bones.
A roller coaster? If someone makes a roller coaster?
Well, a roller coaster wouldn't go.
Under the ground?
Well, I guess some of them do. Yeah, so roller coaster could work. Someone's a roller coaster up here. What if it's a bird?
Mr. McMillan, yeah.
Hey, what if it's a bird going under the water to get a fish?
Or someone's skydiving?
Right?
Scuba diving.
What examples in here? A rocket. Oh, hold on. That's not. Oh, that's the thing. Okay. So here we could dip under the ground, right? We could dip under the ground like a bird going underwater to get a fish. We could any situation where you start on the ground and then end back up on the ground, right? That would be hitting the x-axis twice, right? So like a rocket ship leaving the Earth coming back, you kicking a soccer ball, it's on the ground, you kick it, it's back on the ground, right? Hitting a golf ball,
A rainbow.
a rainbow, Well, you can't really put. No one knows where the rainbow X. It doesn't actually touch the ground. It's more afloat.
It's a optical illusion.
Okay. So anything that starts on the ground and then ends up back on the ground would be a situation. What about never touching the x-intercept? How about no zeros?
Sorry.
What could possibly,
An airplane.
like an airplane dipping and going back up? That would be nice. That doesn't touch the ground, right? So an airplane dipping would work.
A bird.
A bird dipping and it's not going underwater
Yeah.
or not hitting the ground. Yeah.
Uh,
Lots of things.
Curveball.
What about a person bungee jumping? Another situation you would hope they don't touch the ground, right?
Oh, I saw one the other day where the bungee stuff.
I know. But if someone's jumping off a platform, right, and they bungee jump, they come right back up,
Or I just don't do it.
they don't touch the ground, okay? So pick a situation. Hey, if you don't like bungee jumping and you like the bird diving instead, do that one. I don't care. Pick which one you like the
I want to pick
best,
wrestling move.
okay? It would have to be something where you don't touch the ground. You do not start on the ground, you don't touch the ground at all, and you end up back up. Like there's no, doesn't work that way. I need you to pick a real life situation. Do you have another one?
No, yeah, like you know how like they have like indoor skydiving.
Mhm.
You can like go down and then go back
Mhm.
up on the
Yeah.
Oh, I did that. Where they do that, where they laugh.
It's really fun.
It's like a vacuum. It's like
Good.
It's a vacuum and then they take all that stuff.
Good. You're gonna see a lot of these when it comes to physics. If we ever take that science class, quadratics are all over the place. There's a whole lot of they're called projectiles, throwing things and stuff. You're gonna see it used as a business model. So if you want to own your own business, or you can be the person they hire to analyze their business, you know. So you're gonna see how it can get used there also. All right. To solve a quadratic, we look for the what of the graph. What were these points called? The
X-intercept.
the x-intercepts. Good. Which means we see where the graph crosses which axis? The x-axis. X-intercepts are on the x-axis.
I wasn't right.
So solutions. To solve a quadratic, we're looking for the x-intercept on the graph. Those are also called zeros. It's where we cross over the x-axis. Okay? So if I give you a graph like this guy, think for a second, what are the zeros? Don't talk, just think. Look at that, don't talk. Just think. What are the zeros? All right, who wants to answer? Who has an idea? What if I ask you what are the solutions? What? Yeah, 2 and 5. Good. Zeros, solutions, and x-intercepts, they're all the same thing. So asking you what the zeros are, we're looking where does it cross the x-axis. It's crossing over at 2 and 5, but how am I going to write those as a coordinate point? What and what? 2, 0, and 5, 0. That shows the point. Because remember, a 0 is when y is 0, so it's showing you that in the coordinate point. Okay. I would even put a little X on them or put a dot on them so you know what you were looking for on that graph. Are we good? Is 8th grade coming back? Do you remember? Did you do any of this in 8th grade?
No.
Not really? Equations? Okay.
My teacher literally said it would have been the same thing, but it's not.
Okay. All right. This one you're going to work with your table. You're going to have about 1.5 minutes, okay, to talk. Okay. You are going to talk with your table. You're going to look at Aaron's experiment, okay? What type of function best fits the model of the rocket? So you're going to say, should it be a line or should it be a parabola? Talk to each other. Then you're going to say how many seconds did it take to hit the ground and the maximum height of that rocket. Okay? So you have about a minute and a half. Talk to each other. All right, let's see here. Zeke, did you say it was best to use the line or a parabola for this rocket? A parabola, good, which is a quadratic function. How come? Because it curves. Yeah, absolutely. Good. We should use a quadratic function because the graph is a parabola. Very good. Harley, after how many seconds did the rocket hit the ground? 5. There we go. Good. 5 seconds. Don't leave him naked. Sierra, what was we made eye contact. I'm sorry it happened. Estimate the maximum height of my rocket.
6.125 meters.
Okay, 6.125 meters. Good. What do you think, Mason?
I just said 6.25.
6.25 meters. I would take either one of those. You are estimating, so I would take either one of them. Okay, good. But you did have meters on it, which is important. Beautiful. I saw good things when I walked around. All right. So the maximum or minimum point is called something like that. The highest or lowest point of a parabola has a fancy name. What is that point called? It starts with a V. Who thinks they know? What?
Variable.
What'd you say? I was close though. Vertex. Yeah. It's the vertex. Good. Yep. All right. So that point where it is turning, your maximum or minimum point is called the vertex of a parabola. All right, you ready to beat the test? Beat the test. All right, here we go. Jordan owns the business. Here's the business model. All right. During her first year in the business, she collected data and created the following graph showing the relationship between the selling price of a certain item and the profit of that item. Okay, so what she sold it for versus how much profit she got off of it. So what you and your table is going to do, I want you to circle the zeros and then put in words what they represent. So you should use the words profit or selling price when you're using words. Then you're going to draw a box around the vertex. And you're going to say in words what the vertex means. Again, you're going to use selling price and profit when you're describing it. All right? I'll give you 2 minutes again. Maybe, if my phone works. Come on. There we go. Ready? Go. All right. So, Vontae, we just talked about it, so I'm going to call you. Where did you circle the zeros? 10 and 60. Good. All right. Using the words selling price, profit in a sentence, what does that represent with this business? Who has an idea? It's money, but what is it specifically here? What do you have, Mason?
The net profit you mean?
Not yet.
Oh,
Not yet.
dang it.
Jenny.
The selling price in dollars?
It's the selling price. It's the selling price of the item when the profit is. Someone over here had it. Did you have it? Is when the profit is what? 0. Yes. So this is the selling price of the item when you don't make any profit. So in her business, should she sell her item for $10 or $60? Whatever the item is? No, she should not pick that price because she didn't make no money. Okay? She should not sell it for $10 or $60. She made no profit. All right, Shauna, where did you... Oh, it's already up there. Never mind. The vertex box is already up there. So Mason, coming back to you, what does the vertex show?
Net profit.
Yes, this is the maximum profit. Okay? This is showing when she's making the most money. So, how much should she sell this item for?
60.
No? 60, she'd make no money. 35. About $35, right? So when we're all the way at the top, for what? $12,000 in profit? is when she sold that item for about $35. Yes, sir. Yeah. Questions on solutions, zeros, what they represent. All right, so listen, on your worksheet in a minute, it's going to ask you questions like, what do they represent? What does this mean? You shouldn't say anything about, oh, the x-intercept. I want to know in relation to this situation. All right, so make sure you always relate back. So this one was about business. So it was all about profit and selling of a price. Okay? I have your summary question up here next, so that long piece of paper should come out. Today's date is 1/8/20. The section is 5-1. Yeah, they're going to be different each day. We won't do it every single day either. So remember, you got to get a stamp by doing it now.
What's the section?
5-1. Our section is 5-1. So the question is that, so you're going to write down the question, then you're going to answer it. When you're done, raise your hand. I will stamp you, and then you'll work on your half sheet, okay? Keep those phones away. Don't do it. Don't do it. Question is, how are quadratic functions different than linear functions? Okay, so that's what you're writing, and then you're going to answer it right next to it.